Welcome back to Physics 142. We've been talking about inductors and this idea of self-inductance. Basically, the idea is that if you have a circuit, it can still induce a sort of back circuit, a back EMF, if you have changes in the current flowing through that circuit. And so we realized we have these things called inductors, and their job is to oppose rapid changes in a circuit. And so we wrote some formulas down for that. We defined the inductance to be the ratio between the current and the flux through our inductor, through all of the loops of wire in that inductor. And we realized that we could calculate the EMF, or the potential, across that inductor as this inductance, L, times the rate of change of the current. We also wrote down a formula for the energy stored in an inductor. We realize inductors store energy, and the amount of energy stored depends on the inductance and the current running through it squared. So those are sort of the formulas that we have for inductors, and in this video I want to do an example calculation for an inductor, and I want to do a sort of a fairly complicated example where we deal with something called a toroidal solenoid, and we're going to want to find the magnetic field, the inductance, some induced EMF, and the energy stored in this toroidal solenoid. So let's see what I mean by that and see if we can work through this and understand this. So, all right, what is a toroidal solenoid? So solenoids, remember, are wires where you have many loops, right? If you have many loops, we call that a solenoid, right? And that usually solenoids have magnetic fields that run through them, right? That's the idea of a solenoid. Now, toroidal, a torus, is basically something sort of like a donut, right? So if I want to do a toroidal solenoid, what I should do is let me sort of draw my best impression of a donut, except it's going to be a donut with a really big hole and sort of a thin outer layer here. All right, and let's pretend that's uniform. So maybe it's more like a tire or something like that, right? And we're going to give some dimensions here. Is we're going to take and we're going to call this the radius of our torus, all right? So we'll call that radius there, and I'll just have it be to the center, all right? I'll have it be to the center of this sort of outer ring. We'll have that be the radius, and maybe it's useful to, choose some values, so we'll have the radius be 4 centimeters. And then some other things that might be useful is that, well, we're going to have, it's not just a torus, but then to actually make it a solenoid, we want to have wire wrapping around it, right? So maybe this is a little better, right? So we're going to wrap wires around that donut, all right, all around, lots and lots of wire. Okay, drawing here, not exactly the best, but hopefully you get the idea, right? So we're going to wrap wire. We're wrapping the wire all around this solenoid. And so each loop of the wire, right? Each loop of the wire is going to have some cross-sectional area to it, right? There's going to be some area that each loop of that wire, if I sliced through the donut there, right? There'd be some cross-sectional area, and so we'll call that A. And we'll pretend that that is 6.25 centimeters here, all right? So we'll give that a value as well. And let me see if I am doing this correctly. Yeah, okay. So there we go. And so let's see if there's any other dimensions or variables that I need to write down here. Well, we need to run some current through this, right? So let's run current through the wire, all right? So we'll be running current through the wire, and the current, I think it'll be running this way, and the current will run some current I. And let's take that current initially to start to be, let's pick a value let's pick 3 amps, all right? So 3 amps of current initially running through that wire. Okay, so the first thing we need to do is I'm interested in what's the magnetic field in this toroidal solenoid. And this is actually, to find the magnetic field, that's a bit of a review question, all right? Calculating magnetic fields, none of these formulas here explicitly help us calculate magnetic fields, right? The formulas that we had for calculating magnetic fields were Ampere's law and the Biot-Savart law. So that was how we calculate magnetic fields. Remember that the Biot-Savart law was this sort of complicated integral, and Ampere's law applied more in cases where we had nice symmetry. And this is definitely a case where we have some nice symmetry. If we think about what we expect the magnetic field to look like here, right? What do we expect the magnetic field to look like? Well, we know that through a current loop, that magnetic field should go straight through a current loop, right? And if the current's wrapping around like this, the magnetic field would go that way, right? So each of these current loops, we expect to have some magnetic field running through the current loop. So we expect that the magnetic field should actually loop through and sort of run through the center of this torus here, right? Through our solenoid. That's sort of our expectation of what the magnetic field looks like. And this is really nice and symmetric here. Okay, so really nice and symmetric. And so yeah, let's go ahead and see if we can use Ampere's law to do this calculation. So, okay, do we remember what that is? This is good, like, sort of final exam review here, right? Ampere's law, how did that work again? Right, well, what Ampere's law said is that if you draw some loop, right, and you take a walk through a B field, right? Draw some loop, take a walk through the B field, that whatever loop you draw, if you look at the current that you enclose, all right, the total sum of your walk of B dot dl is going to equal mu naught times how much current you've enclosed. All right. So how is that going to help us here with our torus? All right. Well, to think about that a little bit, what I want to think about is, let's just sort of look inside the torus for a second, right? And let's think, let me just think about it like a little piece of the torus here, right? So if I'm thinking about this little piece of the torus, if I kind of, zoom in here a second just to understand what's going on, all right? If I zoom in there, what I'm going to see is that on top of the torus here, I have some current coming out of the page, right? So I could, there's sort of the top of the torus, and it's got a bunch of current coming out of the page, right? And on the bottom here, we've got a bunch of current that's going to be flowing into the page, right? A bunch of current that is flowing into the page, right? Maybe that's a little difficult to see, right? But each of these current loops coming out of the page and then going into the page, right? So that's what sort of each current loop is. And if I did this right, this would have some nice curvature to it, right? And so if I want to sort of, think about then where the magnetic field is, well, the magnetic field is in between this, right? The magnetic field is in here. All right, so there's my magnetic field B. And so, okay, how then am I going to actually figure out what B is? Well, I want to imagine a path, walk some path where I'm walking along B. And so what would be a good path for walking along B? Well, a good path for walking along B is going to be to walk right in the middle, right? I'll walk right along with B, and I'm going to end up walking all the way around, right? I'll walk right along with B all the way around through all of these loops here, all right? That's a closed path. So I can do that, all right? And if I do that, well, every step that I take along the path, if I draw on some DL vectors, right, some DL vectors, they're always going to be in the same direction as B. So then if I go ahead and I do my sort of next step, when I do the dot product, I have B times DL times the cosine of the angle between them. The angle between them is always going to be 0, all right? And that will be equal to mu naught times I enclosed, all right? B is going to be the same everywhere in the loop because of the symmetry, so B will come out, and so then I'll just have B times the integral of DL cosine of 0 is just 1, right? Is mu naught times I enclosed. And what is the integral of dl here? Well, if I imagine that I'm just walking through the middle here, or really, anywhere in here, then the integral of dl is just the circumference of this circle, which is just 2 pi times r, right? So I have b times 2 pi r is mu naught. And now I have to figure out how much current have I actually enclosed in this big circle, right? How much current have I enclosed? Well, that's a good question. Well, each current loop, right? Each current loop has current I going through it, right? 3 amps going through it. And so if I look here, right? If I look at what's enclosed, I have a bunch of wires going into the page, so to speak, right? In my loop going into the page, and every current loop has current I, right? Every current loop has current I going through it. And so if I have n current loops, and so maybe we should choose a number of current loops here. Let's say we have n current loops, and we'll have n loops of, let's say 500 loops, all right? Let's say we have 500 loops. So I enclosed then is then just going to be, well, how many i's do I have? Well, I have n of them, right? N times I. That's my I enclosed. And so then if I go ahead and solve for b, then what I end up getting, if I solve for b, is just mu naught times n times I divided by 2 pi r, where the direction here is just, through the loops, right? Through the loops. All right, so there, that's my B field. Now, one thing I should note that I've sort of assumed here is that I've assumed that this radius is sort of big enough that any little differences in curvature on the inside and the outside of this loop are sort of negligible. All right, or thinking about sort of the radius of this is sort of small enough. The radius of the outer part is small enough that I can do that. But more or less, this is a very good approximation of what that field will be really anywhere inside of that loop. So, all right. Wow, that was a throwback, and hopefully you had some fun remembering how Ampere's law worked. All right. But really, I did that, what we really are interested is in inductors. That's what we've been dealing with. And, but this magnetic field formula is something that I'm going to need in a little bit. So it's useful that we calculated it. So, all right, we found B. Check. The next question is, well, what about the inductance of this solenoid, right? This is something that has a specific geometry. It has a specific area. And so we should be able to work out what the inductance is, right? Because the inductance is something that tells us, basically about the geometry, right? How much flux do you get through the inductor for a given amount of current? So we can calculate that. So let's go ahead and do it. All right, so let's maybe make a little bit more room here. Make sure we can see what's going on. All right, so next goal is we want to calculate the inductance, L. All right, so what is L? So this was finding B. Now we want to find L. All right, and to find L, well, sort of a formula that might be useful is this one that sort of defines L, right? We have that phi here, phi B equals L times I, right? Where this is the flux through our solenoid. And, this is the flux through the entire thing, right? Entire coil, right? The whole solenoid. Sometimes it's useful maybe to split this up a little bit to just think about the flux through each individual coil, right? And if we do that, well then, that would be this total flux is going to be the number of loops times the flux through each individual turn, right? So maybe I say through each single turn. So that might be a little bit helpful. And, well, what is the flux through a single turn, right? Could we figure out what that is? Well, remember that flux is the integral of B dot dA, right? And so for each of these turns, right, we've got magnetic field going through it, B, right? And we think of it as having some area vector that sticks out the center, right? And that's dA. So when we do the dot product, we're just going to get B times dA times the cosine of the angle between them. And we're assuming that roughly B is just uniform through, I guess I should do that with red, it's just uniform in this whole area. And if we make that assumption, then we can just write this as going to be B times the integral of dA times 1, the cosine theta, and the integral of dA is just the area of the thing. All right? So for each turn, single turn, for each turn, we get B times A as the flux, right? And that's roughly going to be the flux. So if we plug that back in over here, we now have a formula that says that L times I is going to be N times B times A, right? Where A is the area of a single turn, right? B is the magnetic field through that turn. N is the number of turns that we have. I is the current, and L is what we're solving for, the inductance, right? So, all right, we're getting close. Let's go ahead and divide by I. So now we're going to have L is NBA. Don't we wish that they could play right now? Okay, sorry, an unnecessary quarantine joke from when I'm recording this video. But all right, N times B times A divided by I, that's going to be L. But so let's see, A we know at 6.25 centimeters squared. All right, squared, there you go. And so 6.25 times centimeters squared. And so we know what A is. We know what the current was. So that's fine. We know that we have 500 loops, but what's B, right? We don't know what the magnetic field is, except we just calculated what the magnetic field was. We just calculated that right up here, so we can now take and plug that in here. So let's do that. So if I plug that in, I'm now going to get NA over I times this expression here, mu naught times N times I over 2 pi R. All right? And, well, now let's see what happens. Well, it looks like I cancels out, and that actually should make some sense because we know that inductance shouldn't depend on how much current. Inductance just depends on the geometry. It just depends on the number of loops, the area, and the radius, so that makes some sense. And so now we have mu naught times A times big N squared divided by 2 pi little r. That's going to be our inductance. So you can go ahead and plug in some numbers for this if you want, right? We could plug in numbers, and if you do that, you know, I think mu naught, that's 4 pi times 10 to the minus 7. The area is, or sorry, the number of the area, this is a little tricky. Several people got messed up on this in their homework, right? 6.25 centimeters squared. How many meters squared is that? Right? Well, you need to convert a factor of 100 twice, right? So that actually ends up being a factor of 10 to the 4. So it's 6.25 times 10 to the minus 4 square meters is 6.25 centimeters squared, right? And then we have 500 turns, and that's going to get squared. And then we're going to divide this all by 2 times pi times 4 centimeters, 0.04 meters, all right? And if you plug all that together, the answer that I got was 7.81 times 10 to the minus 4 henries, all right? And one way to work this out is that another way of writing the units of mu naught ends up being 1 Henry per meter. All right, and I'll let you sort of work through units and see if you can find that one, but another interesting way of writing this. All right, so what you end up getting is 7.81 times 10 to the minus 4 henries is the inductance, that's L, for this toroidal solenoid. All right. Great. So we found L. Check. Now, just a couple more other things that we could find is, well, if we just have a steady current, 3 amps, what's the induced EMF? Right? That might be a question. Well, if the current is steady, if you don't have any change in the current, then the inductor is not going to do anything, right? Then you're going to end up inducing 0 volts of EMF, right? Or 0 amps of current. But now, well, let's say instead we start at our 3 amps, but then we uniformly turn it off. So we're going to decrease from 3 to 0 amps, all right? So let's do one more little situation here. All right, so now let's go ahead and say we want to have our current I go from 3 amps, so it started at, down to 0 amps. All right, and we'll do it pretty quickly, all right? It'll go uniformly, but let's do it in 3 milliseconds, right? So, basically we turn off the current, it ramps down over 3 milliseconds, and we want to know what is the self-inductance of the coil, all right? What is the, the induced EMF in this coil? And, well, we can figure that out, right? Because we had a formula for induced EMF. Our formula for induced EMF was minus L times the change in current, right? Minus L times the change in current. And well, we just figured out what L is for this toroidal solenoid, so we can plug that in, right? Minus 7.81 times 10 to the minus 4 henries. That's L. And what's our change in current here? All right, well, our change in current, our final current is 0 amps. Our initial current is 3 amps. And it took 3 milliseconds, so that's 3 times 10 to the minus 3 seconds, all right? And so if we then take and plug all that in, right, our change in current is negative, right? And we want to do the opposite of that, so that means we're actually going to supply some positive potential in this case, and it actually ends up coming out to plus 0.781 volts worth of potential get supplied, right? So if you go in the direction of the current, you're going to gain some potential, right? The inductor here says, don't turn off, right? Let me give you a little extra boost. And so going in the direction of the current, you actually gain some potential here, all right? If you're gaining some potential, that means the inductor must be supplying you with some energy, right? So, here we're gaining potential in direction of current. Okay, if we want to know how much energy it takes to do that, right? Like the inductor must be giving us some energy if we're gaining potential. Well, how much is it giving us? Well, we can calculate that, right? We have a little energy equation, and so we can write that down, our equation for the energy in the inductor. In this case, it's the energy supplied by the inductor, right? Because it's giving us potential. Well, that's 1/2 times L times the current squared, right? And really it's sort of the change in current, right? How much current change have we gone through here? And so if we do that, it's 1/2 times our L, 7.81 times 10 to the minus 4 henries, all right? And the current here, well, that was 3 amps worth of current, right? Is what we started with. Technically what you say is, well, we originally had, 1/2 times 7.81 times 10 to the 4 henries times 3 amps of energy stored in it, right? And then we sort of released all that energy when we went down to 0, right? We gave that energy to you, and how much energy did we give? Well, that ends up being 3.5 times 10 to the minus 3 joules, I believe, if you calculate that together. So there you have it. Bunch of different things. We now found, the induced EMF, and we found U. Is that even still in my camera? No, you can't even see that. So let's just go back. Right now we found, so for this toroidal solenoid, we did a lot. We found the B field. We found out then from its geometry what its inductance was. Then we figured out what sort of when we turned it off, how much potential we induced in the system, and finally we found out how much energy it took to give us that potential. So lots of different things to calculate here, and hopefully this is helpful to you as you do some of your own calculations.